In this tutorial, we're going to design the open channels required to canalize the rainfall for urban zone. When we go to perform a hydraulic design, it's better always do it in this order. First, the open channels. Second, the clean water system. And finally, the sewer system. The reason of this is because the interference that could occur during the construction phase. For open channel design is considered the optimal return period of 10 years the best options to perform the design. The first thing to do is analyze the runoff based on the topological contours by tracing perpendicular arrows in each contour, which will represent the directions of the runoff and will help us to understand how is the behavior of the runoff. After that, we trace a preliminary open channel to collect the rainfall according with the requirement of the project. The next step is divide in areas the different sections of the channel to determine how much rainfall will collect each section according with the runoff already analyzed. Now we can proceed to calculate the design flow that will receive each section of the channel using the rational method, as described in section 9.5.4 of the AASHTO Design Manual, where Q is the design flow, C is the runoff coefficient according with the table 9-4 of the AASHTO Design Manual, normally taking as 0.19 for concrete areas, 0.85 for asphalted areas, between 0.1 and 0.35 for non-residential ground areas, depending on the slope of the terrain and the type of vegetation, and 0.6 for apartment dwelling areas. I is intensity, duration, frequency of the rainfall IDF. This value is calculated through charts that depends on the Meteorological Institute of each country. In this example, I will use a generic one. The time of concentration is taken according with the section 9.5.6.2 of the AASHTO Design Manual, as 5 minutes for paved areas and 10 minutes for unpaved areas, giving a result of 6.23 inches per hour for unpaved zones and 7.53 inches per hour for paved zones. And A is the area that affects the analyzed section in acres. In example, for the section between points A1 and A2, result in 0.499 cubic feet per second. With the design flow already calculated, we proceed to determine the dimensions of the channel required to canalize the flow of the rainfall using the continuity equation and the Manning equation, in accordance with equations 10-4 and 10-5 respectively. After make some substitutions and reorganizing the equation, this is its final form for a U channel, where N is the Manning roughness coefficient, equal to 0.015 for concrete lining channels, in accordance with the table 10-5 of the AASHTO Design Manual. S is the slope of the section analyzed, B is the width of the channel, and H is the height of the flow. The process is based on fixing the width of the channel and itinerate with the height of the flow until both sides of the equation have the same value or are approximated. It's important to mention that the design is controlled by two factors, the sedimentation and erosion. To avoid the sedimentation, the minimum velocity is 3 feet per second, and the minimum slope is 0.3% in accordance with the section 11.3.2.8 and 11.4.6 of the AASHTO Design Manual respectively. And to avoid the erosion, the maximum velocity for concrete lining channels is 20 feet per second, according with the section 11.3.2.7 of the AASHTO Design Manual. In example, for the same section, we fixed the width of the channel to 1 foot, and the height of the flow after iteration is 0.096 feet. The velocity is checked with equation 10-5 of the AASHTO Design Manual, where RH is the hydraulic radius calculated by the wetted area divided by the wetted perimeter, giving a result of 5.15 feet per second, and the slope is 7.77%, both verification passed. This process shall be done with each section of the proposed channel. The final height of the channel depends on the topography of the terrain. In this table are the results for the channel A, and in this figure is showed the final design of the channel. With this conclude this tutorial.